The world of AI is moving incredibly fast, isn't it? And one of the most exciting frontiers right now, I think, is models that can understand not just text, but images, video, the whole multimodal spectrum.
Absolutely. It's
Okay.
where AI starts to really perceive and interact with the world around it.
Yeah, it feels like a big step.
It is. We're moving beyond just language processing into systems that can genuinely reason across different kinds of information. Acting more like agents, really, in digital or even physical spaces.
Mm.
It's a field that really started picking up steam foundationally back in the early 2020s, building towards what we're seeing now.
And speaking of what's emerging, we've got something pretty interesting to dive into today. MiMo-VL7B. It's a new vision language model from Xiaomi.
Right.
And it's making some significant waves, apparently, especially considering its size.
Yeah, we've got the official technical report for it right here, plus some useful development notes that you, our listener, actually shared with us.
Great. So our mission for this deep dive is to really unpack this report. We want to get past the headlines, understand the innovative training techniques, and crucially, those key academic insights the researchers are presenting about why these techniques actually work so well.
Right, the mechanics behind the performance.
Exactly. Think of this as your shortcut, basically, to grasping the core ideas driving MiMo-VL7B's state-of-the-art results.
Okay, let's get into it.
Yeah.
So at its heart, MiMo-VL7B is a vision language model, a VLM.
Right.
And like we touched on, VLMs are, foundational for these multimodal AI systems. They let the AI process and understand information that spans different types, like seeing an image and reading text about it, then answering a question that needs both.
And this one's described as compact yet powerful. So what's under the hood? What's the architecture like?
Well, it's basically built on three main parts. First, there's a vision transformer encoder, a VIT, and it's designed to process visual stuff, images, video frames at their native resolution.
Okay, why is that important?
Because it means the model doesn't lose those fine-grained details right at the start. It's not compressing the image down too much immediately. It gets a clearer picture, so to speak.
Right. High fidelity input. Makes sense.
Exactly. Then that visual information goes through a multi-layer perceptron, an MLP projector. Think of this as the bridge.
Okay.
It translates the visual features coming from the VIT into a format, sort of a shared language or latent space, that the language model part can actually understand and align with text info.
Got it. So it's making the visuals speak the language model's language.
Precisely. And the third piece is the language model itself. They call it their MiMo-7B backbone. And this part, according to the report, is specifically tuned for handling complex reasoning tasks.
So you've got sharp eyes, a translator, and a brain built for tough problems.
That's a good way to put it.
And the report mentions two main versions coming out of this. MiMo-VL7B SFT, which is from the initial training.
Right, the supervised fine-tuning stage is essentially built on the pre-training.
And then MiMo-VL7B RL from post-training using reinforcement learning.
Correct. And the results they're reporting, especially for a 7 billion parameter model, are, well, quite impressive. They're claiming state-of-the-art among open-source models of similar size.
Even beating some bigger models on certain benchmarks.
Yeah, on some challenging ones. So the big question is, how did they pull that off? And that's where the report really dives into their training methods, highlighting some key innovations.
Okay, this is where we get into those academic insights. The training journey, they say, has two main phases. Phase 1 sounds intense, a 4-stage pre-training process using a massive 2.4 trillion tokens of data.
Yeah, that's a huge amount. The goal there is building that foundational multimodal capability from scratch.
And it's structured.
Very structured. Stages 1 to 3 progressively build skills. Stage 1 is about getting the vision and language parts talking basically image caption alignment.
Okay.
Stage 2 brings the vision transformer fully into the training loop, unfreezes it, and uses interleaved image text data for, stronger alignment. Then stage 3, they open up all the model parameters and through a really diverse mix of data at it. Things like OCR data, object grounding, video understanding, even GUI interactions, and text-only data, too.
Wow, a bit of everything.
Exactly, to create a general-purpose multimodal base. They really emphasize the careful curation and diversity of data in this phase.
Okay, that makes sense for building a wide base. But the report specifically flags stage 4 of pre-training as a key innovation. What's special there? Why is it so important?
Yes. This is where they highlight a major innovation and really an academic finding from their work. Stage 4 is focused on two things. making the model better at handling long inputs, extending its context window, and critically, fully unlocking its reasoning abilities.
Longer context and better reasoning. So what's the novel part?
The core innovation here, according to the report, is adding a markedly increased proportion of high-quality synthetic reasoning data that features long chain of thought, or COPE. And they incorporate this directly into this late stage of pre-training. They didn't wait for a separate fine-tuning step later on. They baked it in when the model was already pretty capable.
Why is that timing and that specific type of data so crucial? This sounds like one of those core academic takeaways.
It really is. The report discusses this insight quite clearly. They found that relying too heavily on traditional, often shorter, question-answering data can sometimes just teach the model superficial pattern matching.
Like memorizing answers without understanding.
Exactly, like teaching a student just the final answer without showing the work, It doesn't lead to deep understanding or the ability to generalize that reasoning.
Right.
But by explicitly training with this synthesized data that has long step-by-step chain of thought reasoning laid out, well, that gives the model much richer supervisory signals.
So it forces the model to actually learn how to break down problems.
Precisely. How to follow logical steps, how to generalize the reasoning patterns. And the key finding here, which they back up with data in their figure 6, is that putting this kind of data in late pre-training significantly boosts performance. And importantly, it shows continued improvement without saturating in that stage, unlike maybe other data types might.
So the big academic takeaway for someone developing these models is the kind of reasoning data, its structure like long COTI, and when you introduce it, matters a lot. It's not just quantity, it's quality and timing.
That's exactly it. It's about guiding the model's process of thinking, not just the outcome. And they were careful about it, too. They used powerful LLMs to generate initial drafts, regenerated them for detailed COTI, and used rejection sampling to keep the quality high. Very deliberate.
Okay, so stage 4 pre-training gives a big reasoning boost. What about phase 2 then, the post-training phase?
Right. Phase 2 uses what they call a novel framework, mixed on-policy reinforcement learning, or MoreRL.
MoreRL. Okay, what's the goal with this phase?
The aim here is to further refine the model's abilities, especially on those really challenging reasoning tasks, but also to improve how well it aligns with human preferences, making it more helpful and natural to interact with.
And MoreRL achieves this by mixing different kinds of reinforcement signals.
Exactly. It combines two main components. First is RLVR reinforcement learning with verifiable rewards.
Verifiable rewards, like rewards based on whether the answer is actually correct.
Yes, precisely. This uses objective, often rule-based rewards. They applied it to tasks where you can check correctness programmatically. Think visual reasoning in STEM, text-based math problems, image grounding using metrics like intersection over union,
GIOU,
visual counting, temporal video grounding checking segment overlaps. If the model gets it right or very close by these objective measures, it gets a reward.
Very concrete. What's the other component?
That's RLHF reinforcement learning from human feedback. This is where subjective human preferences come in.
Okay, so things like helpfulness, clarity, safety.
Exactly. Overall quality. They collected a diverse set of queries and had either humans, or sometimes a powerful VLM acting as a proxy, rank different model responses. Then a reward model is trained on these rankings to provide that RL signal.
So you're blending objective correctness rewards with subjective preference rewards using RL.
That's the mix in MoreRL. And apparently they built this sort of reward as a service system to manage all these different reward types efficiently during training. Low latency, unified interface.
Now, the report makes a point about the type of RL they used, calling out the on-policy aspect as another key academic insight. What's that about?
Yes, this is the second major academic finding they emphasize, and it's really about the scalability of the RL training itself. They adopted an on-policy variant of GRPO. GRPO is an algorithm used for policy optimization in RL.
And what did they find about using this on-policy version specifically?
This is pretty significant for the research community, I think. Looking at their figure 7, they explicitly show that the performance using their on-policy RL approach keeps improving as they feed it more training data.
Okay, and how is that different from other ways?
Well, they contrast it with what they term vanilla GRPO, which might represent a more standard or perhaps off-policy approach in some contexts. Vanilla GRPO, while maybe good initially, hits a clear performance saturation point in their experiments.
Meaning it plateaus. More data doesn't help after a certain point.
Exactly. It kind of levels off, even if you keep feeding it more data beyond, say, 20,000 samples in their chart. but the on-policy version just kept climbing.
Huh. So the academic insight is that choosing an on-policy RL method, like their GRPO variant, seems to unlock better potential for scaling performance with more data compared to standard methods. That feels important for pulling model limits.
That's the key implication they draw from those results. It suggests that if you want to achieve really high performance levels through extensive RL training, this on-policy route might be more promising.
Okay, let's quickly recap the two major academic insights from this report then. What are the core takeaways for our listeners?
Sure. First, that strategy of deeply integrating high-quality, long chain-of-thought reasoning data, specifically in the later stages of pre-training, is really powerful. It genuinely enhances deep reasoning, moving beyond just surface-level knowledge.
And they saw evidence of that.
Yeah, like the average response length on hard benchmarks like MMMU jumping from around 680 tokens to 2,500 tokens after this stage, that suggests much deeper step-by-step thinking.
Right. And the second key insight?
That comes from the post-training. Their mixed on-policy reinforcement learning framework works well, but specifically, the on-policy RL variant shows superior data scaling. It keeps getting better with more data, unlike the vanilla methods they compared against.
But they were also upfront about a challenge there, right, in the more Morel phase?
Yes, and this points to an active research area. They note that getting stable simultaneous improvements across all the diverse tasks in Morel is tricky because of interference.
Meaning optimizing for one task might hurt another.
Kind of. Different tasks can have conflicting optimization signals. For example, long detailed explanations are good for reasoning tasks, but maybe short direct commands are better for GUI grounding tasks.
Ah, so optimizing for verbosity versus optimizing for conciseness, potentially.
Exactly. They observe these conflicting trends and difficulties in simultaneously perfecting everything. It's not really a flaw in their method per se, but an honest reporting of a known challenge in complex multi-objective RL highlighted by their experiments.
Okay, so these training innovations and academic findings sound great in theory. How does it actually translate to performance on benchmarks? What do the results tables show?
Well, the report presents a lot of results. Tables 2 and 3, figures 4 and 5 are key. And for a 7B model, MiMo-VL, especially the RL version, really does show state-of-the-art performance among its open-source peers.
Where does it shine, particularly?
The report highlights SOTA results on general perception and reasoning benchmarks compared to other open-source VLMs around that size. And importantly, it outperforms even some much larger models on really tough academic tests like MMMU and Olympiad Bench. Those require serious multimodal understanding and reasoning.
And what about that GUI grounding you mentioned earlier?
Yeah, that's another standout area.
Yeah.
They set a new benchmark standard on tasks like Oswald G, showing really impressive accuracy in understanding and interacting with graphical user interfaces. Their scores are comparable to, or even better than, models specifically designed for GUI tasks, which is quite remarkable for a general model.
That ELO rating in Figure 5 also caught my eye. That's not just academic scores, is it?
No, that's right. That ELO rating comes from their own internal user preference evaluations. Basically, how much real users preferred its responses in actual interactions.
And it scored well.
Highest among the open-source VLMs they tested, and it was even getting close to proprietary models like Claude 3.7 Sonnet at the time. That's strong evidence that the MRL phase, especially the RLHF part, really did improve usability and helpfulness in practice.
And it's great that they're open sourcing not just the models, but also that big evaluation suite over 50 tasks.
Absolutely. Promoting transparency and giving the community tools to evaluate these complex models properly is crucial for moving the field forward. That's a significant contribution itself.
Beyond the numbers, did the report show any examples of what the model can actually do, qualitative stuff?
Yes, definitely. For instance, Figure 8 shows the model tackling a pretty complicated physics problem, and it outputs a detailed step-by-step chain-of-thought solution. That directly shows the kind of deep reasoning they cultivated in Stage 4 pre-training. And Figure 10 is similar. It shows the model solving a whole multi-part math test, keeping track of context, and applying reasoning across several steps.
What about those agentic capabilities, like using a website?
Figure 9 is a great illustration of that. It shows the model navigating a website interface, understanding the elements, and completing a task like adding a specific item to a wish list, even handling customizations.
Wow.
Yeah, it showcases the practical application of combining that strong visual grounding with reasoning to act in an interactive environment. Points towards its potential as a capable AI agent.
Okay, so wrapping this deep dive up then, MiMo-VL 7B hits state-of-the-art performance by combining, let's see, meticulous pre-training, especially that late-stage infusion of long COT reasoning data,
Right.
and then this novel mixed on-policy reinforcement learning framework.
That really captures the core message from the report, yeah. The key academic findings are the big impact of that strategic reasoning data integration, the promising data scaling properties they found with their on-policy RL approach.
Compared to vanilla methods.
Compared to vanilla methods, exactly. And also that honest acknowledgement that task interference in multi-objective RL is still an ongoing challenge that needs more research.
And the open sourcing helps everyone explore these ideas more.
Definitely.
So thinking about these insights, how critical specific kinds of structured data like long COT seem to be, and how much difference advanced training methods like on-policy RL can make. What does this suggest about the path forward for building truly intelligent, versatile, multimodal AI agents?
Well, it does raise a really interesting question, doesn't it? If this work shows that very specific, carefully chosen data types and particular algorithmic choices in training are keys to breakthroughs in complex areas like reasoning and interaction.
Yeah.
It kind of implies the future isn't just about scaling up compute or throwing ever more generic data at the problem. Maybe the path forward involves more careful identification and leveraging of other kinds of high-quality data, or designing new training signals specifically tailored to foster advanced skills.
Like what other kinds of structured experience or reasoning supervision could we find and integrate strategically?
Exactly. What are those untapped sources or methods that could unlock the next level of performance? That's the provocative thought this kind of research leaves you mulling over.